Welcome to Everything Explained. I'm your host, and today we're diving into a big question. How do we know the age of the universe? It sounds simple. The universe is old. We say it's about 13.8 billion years, but the method behind that number is a story of clues, cross-checks, and patient detective work. We'll walk through the main ideas, from the stars stretching away from us to the faint glow left over from the very first moments. By the end you'll see, the age isn't a single measurement. It's a conversation between several lines of evidence, all pointing to one time when everything began. First clue, the galaxies are moving away. In 1929, Edwin Hubble measured that distant galaxies glow with a red tint that grows stronger the farther away they are. If galaxies are drifting apart, then tracing the motion back in time makes it clear there was a moment when everything was squeezed into a much smaller space. That moment is what scientists call the Big Bang. If you just knew how fast the cosmic expansion is today, you could estimate how long it's been going on, roughly. But the universe isn't a simple, constant speed engine. Gravity slowed things down. Then dark energy started pushing things apart again. So the exact age isn't just one divided by the current rate. You need the whole history of expansion. Next comes the cosmic microwave background, or the CMB. About 380,000 years after the Big Bang, the hot plasma cooled enough for electrons to combine with atoms, and light could travel freely for the first time. That light has been traveling through space ever since. Today we detect it as a faint, almost uniform glow in every direction. Its tiny variations in temperature and pattern tell us how the early universe was built, how much ordinary matter there was, how fast it was expanding, and how long it took for the first structures to form. The Planck satellite mapped these fluctuations with exquisite precision, and, from them, scientists deduced the age, about 13.8 billion years. The CMB is like a baby photo of the cosmos, giving us a snapshot of the universe just 0.000004% old. To cross-check, scientists use other tools that don't rely on the CMB alone. The distribution of galaxies shows a regular pattern called baryon acoustic oscillations. Think of a faint cosmic drumbeat. The sound waves created a preferred spacing in matter that we still see in how galaxies cluster. Measuring that spacing at different distances helps map how the universe expanded over time, adding another line to the age estimate. Then there are standard candles, a fancy term for objects whose intrinsic brightness we understand well. Type Ia supernovae are the best known of these. When we observe them in faraway galaxies, we can tell how far away they are by how bright they appear, which clocks the expansion history. These two support an old universe, and they helped reveal that the expansion is accelerating, not slowing down, a factor that we must include when calculating the age. Even earlier clues come from the light elements born in the first minutes after the Big Bang. The amounts of hydrogen and helium and tiny traces of lithium depend on the density of matter and the rate of expansion as the universe cooled. Matching those primordial abundances with what we see in stars and gas today gives another independent word that fits the same timescale. Of course, there are debates and small tensions. If you measure the current expansion rate in two different ways, a direct, local method using bright objects in our neighborhood versus a method tied to the cosmic background, you don't get exactly the same Hubble constant. That's like two clocks that disagree by a few percent. Scientists are chasing that discrepancy because it could point to new physics or hidden quirks in our measurements. But the age of the universe, pinned by several independent lines of evidence, still lands around 13.8 billion years. So how did we learn it? By reading a chain of clues, the crowded history of galaxies telling us the past motion, the baby light from the CMB telling us the conditions of the early universe, the ripples and candles we use to check the distance and expansion, and the nuclear physics that whispers what happened in the first minutes. Each piece is a separate experiment, but together they point to the same moment far in the past when everything began. That convergence is why we feel confident about the age, even as we keep refining numbers as our instruments get sharper. That's the story of how we learned the age of the universe, not with a single measurement, but with a chorus of evidence, harmonizing to reveal the dawn of everything. So keep looking up. The universe is older and brighter than any single answer, and we're still listening.